Okay, well, we're a couple minutes past the hour. Um, so I'd like to introduce our speaker today. He's coming at us from Boulder, Colorado, and his name is Daniel Slichter. He is a staff physicist at the National Institute of Standards and Technology in Boulder, Colorado. His research focuses on quantum information experiments with trapped atomic ions, with an emphasis on developing new paradigms for scalable trapped ion quantum computing and networking. Among other projects, he and his team are developing microwave and RF-based techniques to perform high-fidelity control and entanglement of trapped ion qubits, along with trapped integrated photon detectors for qubit readout. Before coming to NIST, he conducted research in superconducting quantum information at the University of California at Berkeley, where he performed the first continuous high-fidelity measurements of a superconducting qubit and studied quantum feedback and measurement backaction. These breakthroughs relied on the development and use of near quantum limited microwave frequency superconducting parametric amplifiers, much the topic of last week's seminar. Dr. Slichter received his AB in physics from Harvard University in 2004 and a master's in 2007 and a PhD in 2011 in physics from the University of California, Berkeley. He was a recipient of a Hertz Fellowship Foundation, the Hertz Foundation Thesis Prize, an NRC postdoctoral fellowship, and a Kavli Fellowship. He currently serves as an associate editor for IEEE Transactions on Quantum Engineering. And so with that, it is my great pleasure to have Daniel Slichter give us a talk today on integrating the trapped ion quantum processor. So Daniel, you'd like to appear.
Hi, Nick. Thank you very much for the introduction, and thanks everyone for coming to hear my talk today. I am going to tell you about some work we're doing in our group on trying to integrate the trapped ion quantum processor. I'll explain what I mean by that. First off, I want to point out that this is work that's the product of efforts of many different people. I'll highlight a few in particular. The experiments that were done that I'm going to describe today were spearheaded. Most of the work was done by Raghu Srinivas and Susanna Tadaro, a couple of graduate students. Sean Bird and Hannah Knock, two more graduate students, also played major roles in this work, along with a number of other people as well. There are a number of staff scientists as well in the group who played a role, as well as David Alcock, who is now professor at University of Oregon, but he and I worked together on these a lot as part of our postdoctoral work here at NIST. The theory for the laser-free entangling gates I'm going to tell you about was developed by Tyler Sutherland from Livermore Labs, who's now a professor at UT San Antonio. And then the integrated photon detectors that I'll tell you about, that was work that I did in collaboration with Varun Verma, who's another staff scientist at NIST, in collaboration with Rich Mirren and Sewu Nams in their groups at NIST. So from here, I will move on, and I hope you enjoy the talk. Thank you again, Nick, for the introduction, and to the organizers, to Zlatko and Olivia, for the opportunity to speak to you today. So my talk, I'm going to start out with a brief introduction to trapped ion qubits, just to sort of set the stage for people. Then I'm going to talk about two different projects, one on integrating RF and microwave control of qubits into the ion traps, another about integrating photon detectors into the ion traps, and then finally, I'm going to tell a little bit about our vision towards trying to integrate as much as possible, basically everything that we can, into an ion trap to make large-scale quantum processors. So we'll start off with an intro to trapped ion qubits. So a trapped ion qubit is basically sort of the classic thing that people think about, is you pick two internal energy levels, electronic levels, spin levels or something, of an atomic ion that's trapped somewhere and held in ultra-high vacuum. But that's not the only quantum degree of freedom that we have. There's also, if you have a trapped ion and you laser cool it, you can actually treat the motion of this ion as a quantum degree of freedom. And so these two, both the internal states and the motional states of atomic ions that are held in place in ultra-high vacuum are going to be this sort of the quantum systems that we're talking about today. So why would one choose to use trapped ion qubits for quantum computing or other applications? Well, there are several reasons. One is they're identical qubits that you can hold on to for hours and days. If you have 10 of them, you know they all have exactly the same properties, which can be a nice feature. They can have very long coherence times. So, I mean, this most recent result here of basically dephasing times of close to an hour, basically, which is very nice. You can do very high fidelity state control using laser beams or microwave magnetic fields. And people have shown single qubit gate errors at the sort of 10 to the minus 6 level. And there are now a number of different groups that have shown entangling gate errors, 2-qubit gate errors at the sort of 10 to the minus 3 level. You can measure out, you can read out the state of the qubit with errors that people have demonstrated as low as sort of 10 to the minus 4 readout errors. And this is an idea that was pitched that you could do it this way by Hans Dehmelt back many years ago, almost 40 years ago now. And then another neat feature is that with ions, you can actually on the fly reconfigure the connectivity graph of your qubits, of your quantum processor. And this is something that was pointed out by Dave Wineland almost 25 years ago as well. But, also just from a sort of a scientific standpoint, this is you can have a bunch of coherent, tunable, and couplable spins and quantum harmonic oscillators, which are really nice systems for testing out many kinds of experiments you'd like to do. So I'm going to explain a little bit about trapped ion hyperfine qubits, which are one subtype of trapped ion qubits. In particular, with beryllium-9 and magnesium-25 are the two ion species I'm going to talk about today. And they both have sort of a similar energy structure here. They're both, we've picked these two species because they have filled shells and then there's one valence electron around them. And that makes the atomic physics fairly straightforward of figuring out what the level structures look like. And they're basically, we'll pick two hyperfine states in this ground state manifold here to be our qubit. There are more states that I'm not showing here, just for clarity. And then there's an excited state up here, which for our purposes will be this state. There's actually many sublevels in that too. And if you choose properly which hyperfine states you want to use here, you can pick these so-called clock states depending on the magnetic field. And those can have T2 times of greater than a second without too much effort. And T1 is basically, for all intents and purposes, infinite. So this is not to scale this energy level diagram. The qubit splitting here is sort of 1 to 2 gigahertz. And then this splitting here is an optical splitting. So these are ultraviolet photons for both magnesium and beryllium. Now I want to point out another difference here, which is that the qubit frequency is 1 to 2 gigahertz. But we don't actually have to have a millikelvin apparatus in order to achieve this, because the atom itself, this transition is only very weakly coupled to sort of thermal blackbody radiation. And so that means that optical processes to prepare the state and to cool the ion are actually what we use to prepare a given qubit state. And once you prepare a given qubit state, it will stay there for a very long time. So we're not as worried about the thermal coupling to the environment as far as the qubit states go. So for this laser cooling and optical pumping to prepare the state in a well-defined quantum state, we can use one resonant laser that excites us from this state up to states in this manifold and decays back down and runs around. And as we do that, we can pump and initialize this state here, an emotional state. Now, to control the state of the qubit, there's a couple of ways we can do this. One is we can use two laser beams, which are detuned from this transition here by some reasonable amount, and that have a beat note at the qubit frequency. And so we can drive stimulated Raman transitions between these two levels. Another thing we can do is we can apply a magnetic field just at this frequency here. So I'll be talking about this today as sort of some of the main stuff that we're working on. And then finally, to read out the state of the qubit, we can shine on a resonant laser here that takes you from this level to only one state up here and can only decay back down to exactly this state here. So you'll cycle around and around and around if you're in this state, and you'll scatter millions of photons per second. And if you collect sort of a % or so of those photons, that's sufficient to have high fidelity readout. So the ion will be scattering photons in all directions. And if you actually look through a microscope objective with a camera, you'll see a little glowing dot in the middle of your vacuum chamber. And this is a picture of a single ion fluorescing because it's in this state. Now, this laser was chosen such that if you're in the other state, the other qubit state here, it's not resonant with anything upstairs. And so you don't actually absorb and re-emit photons. You don't scatter anything. So you have an ion that's dark. And you'll have to believe me that this is actually a picture of a dark ion and not just something else. But so seeing the difference between bright and dark is the qubit readout. So you can see this can be done with fairly high fidelity. So how do we hold on to these ions? Well, we hold on to them for the experiments I'm going to talk about with what's called a linear RF ion trap. So it happens if you want to hold a charged particle in place in 3D space. You can't do it with just static electric fields. You can look at Laplace's equation and figure that out. There's a theorem called Earnshaw's theorem that makes this explicit point. But what you can do is you can use a combination of oscillating and static electric fields in order to hold the particle in place. So the way we do this is this is sort of a classic what's called 4-rod linear trap. So you have 4 rods here, 2 of which have an RF potential applied to them, and the other 2 of which have DC potential. So if we look at an end view here, what this is it's not a minimum or a maximum, but it's a saddle point. This RF quadrupole here, it's a saddle point of the electric potential. And so the saddle is flapping up and down at whatever this radio frequency is. And so the point is that at any moment in time, the ion might want to roll over this way. But as soon as it thinks it might roll over this way in the anti-confining direction, all of a sudden that direction is confining. And so if you make this oscillation frequency and amplitude correct, given the mass and the charge of the ion, you can actually get confinement in a dynamical sense for this ion. So it will tend to stay here. And so this will confine the ion in this plane, this cut plane. And then along this third axis here, we can use static potentials to make a well and confine the ions that way. And usually what we do is we make this transverse, this radial confinement tighter than the axial confinement. So the ions, which are charged and repel each other, will kind of line up in a little string along this line here. So this is how a linear Paul trap works. One thing that people are doing a lot these days is taking this sort of 3D Paul trap, and you can actually think about kind of like unfolding it onto the surface. And so now you can make a 2-dimensional trap where if you look in cross section, the symmetry is lower, but you still have this RF quadrupole, which allows you to confine the ions here. And so the reason why you might want to do something like this is now you can microfabricate all sorts of complicated electrode structures to make fancier ion traps than you could if you were sort of 3D machining something. So we have to look now, because we have these ions confined, we have to think about what their motion is doing in this trap that we're holding them in. So really, the ion states that we have are a combination. It's a product of both. There's this spin state, this hyperfine spin state that we're talking about, which has some sort of gigahertz splitting. And then also the motional state of the ion. We laser cool the ions, and the laser cooling gets us down to the point where this motion needs to be treated quantum mechanically. And these motional frequencies are typically sort of on the order of megahertz. So now, when we talk about state transitions, we're going to actually talk about several kinds. One is what we call a carrier transition. In a carrier transition, we flip the spin, but we don't change the motional state at all. You can also have what we call sideband transitions. And the sideband transition will flip the spin and either subtract or add a motional quantum while it's doing that. And these sideband transitions require a gradient. We'll talk about this in a little bit about what exactly I mean by that. So for those who are sort of more mathily inclined, these red and blue sideband transitions correspond to the sigma minus A dagger and sigma plus A dagger and Hermitian conjugate type Hamiltonians. So what can you do with sidebands? So First of all, you can use these sidebands along with repumping lasers to actually cool the motion to very close to the ground state, so basically to n equals 0. And that's something a lot of ion trappers do. The other thing these are is if you look at this, this is a sort of Jaynes-Cummings type interaction for those for whom that means something. This is what you would call an anti-Jaynes-Cummings interaction, which is normally not energy conserving in a sort of a cavity QED or circuit QED system. But because we're doing this with applied control fields, we can actually have it. So the ability to have both of these together gives us some nice knobs in this sort of quantum playground. And if you actually turn on a red sideband and a blue sideband together, you can realize a force on the ion that depends on the spin state of the ion. And that is going to be a building block for things that we'll see later. So here's sort of the spin and the motion. Now, what happens when you have multiple ions in a trap? So, the ions are charged, and so they repel each other. And so they tend to sit, here's a picture of 4 ions in a trap. They sit a few microns apart. And at these distances, the sort of spin-spin couplings between the ions are very weak. They're millihertz. They're far enough that there's no overlap of the wave function, so there's no exchange interaction. So, okay, we've got these nice qubits, but how are we going to get the qubit states to interact like this? And the realization you have to make is you kind of rephrase this repelling each other. You say, no. The motion's just very strongly coupled. So this is the sort of the ad man's version of what it is. And so this means that the eigenmodes of motion actually involve multiple ions. So if you have 2 ions, you'll actually get motional modes that are not just one ion moving, but you'll have eigenmodes that look like this. So here we have axial modes where the motion is along the axis of the ions, and here are what we call radial modes that are transverse to the axis of the ions. And you can have modes where the ions are moving together in phase or where the ions are moving out of phase. But the point is that no matter what, the motional modes all involve both of the ions. And so you can use this mode. So this would be a single, A and A dagger. This would be B and B dagger, C, D, whatever you want to say. You can use those modes that are shared between the ions as a quantum bus between the ions in a similar way to how people might use a cavity as a quantum bus between qubits and cavity QED. So in order to do this, you have to have some way of coupling the spin state of the ions to the motion. And then you also want the motion to be cold. You want it to basically be in the quantum regime, so you know where it is. And a general rule of thumb is that all multi-ion interactions within a trap are mediated by motion. And there are a couple of exceptions. There are people doing Rydberg ions, and you can have photonic coupling between ions. It's generally used between different traps that some people are working on, for example, for quantum networking applications. So how do you scale up something like this? Well, the vision that we've been pushing at NIST now for about 25 years almost is what we call the quantum CCD architecture. And this is something that Dave Wineland proposed in this famous paper here in 1998. And the idea is to make a large scale ion trap with many different electrodes. And so, I've got different zones. You can have some ions that live here and ions that live there, and et cetera. And some of these zones might be dedicated for readout. Some of them might be for memory. You just hold qubits there. Some of them you might do gate interactions in them. And then the idea is that you move the ions around between the different zones when it's time to involve them in different things. So this means you can actually reconfigure the connectivity of your qubits on the fly. You can check a qubit from here and a qubit from there and bring it over there, do a gate, move back, etc. You only need to have control access to some subset of the trap. And then the idea is, you make a picture like this. You could think about if this is planar, you might be able to microfabricate this and scale up that way. And this has actually become a reality. So here are, a series of different traps that have been made, both these two at NIST and these by Sandia and now Honeywell for their commercial trapped ion quantum computing that are basically exactly this quantum CCD vision that's been proposed here. But so this is now actually becoming a reality. But then we want to sort of step back and look at the complete system. So here is one of the ion trap systems in our lab. The trap lives right in here inside this glass vacuum envelope in between these coils. But then there's a whole bunch of other stuff. There's microwave antennas out here just hanging out outside to make fields for the ions inside. There's a giant imaging objective to collect the fluorescence. There's a whole bunch of laser beams that have been very carefully and painstakingly aligned by students and postdocs, different colors and things like that. There's a bunch of lasers on these tables right here. But so all of this, we've got these nice microfabricated scaled chips, but this kind of stuff here doesn't scale as readily if you want to have hundreds or thousands of qubits. And so the question is, could we integrate more of this kind of control and readout stuff into the trap chip itself? It would make it more stable, it'd make it be sort of self-aligned, it could be more compact, and that might improve the fidelity and might also make it more scalable. So this sort of goal of integration is what I'm going to talk about today. What of these things that are out here can we add into the trap and make it work well? So the first thing I'll talk about on that context is RF and microwave control. So as I mentioned, coupling the spin and the motion of ions is really an essential tool for not just quantum computing, but also people doing quantum simulation, quantum logic spectroscopy, which is what trapped ion clocks, a lot of trapped ion clocks rely on. And this requires you to have either a sideband, like I described, or a spin-dependent force of some sort, which can be realized with two sidebands or with other combinations. And basically, what this means in sort of a physical way is you need to have some field that couples to the internal state of the ion, to the spin state, and where there's a spatial gradient of that field. And so you can see many examples here from the literature of different types of experiments where people are doing spin motion coupling, and you can see they all use lasers, right? So this is usually how people achieve this spin motion coupling is with lasers, because lasers have a fairly short wavelength, and so there's usually large spatial gradients that can be achieved as a result. So people have done laser-based gates for hyperfine qubits. So I remind you just quickly of our energy level structure here. We've got the spin and the motion as well, and then we have this sort of excited state, which we sort of detune a stimulated Raman transition from by quite a distance. And then this, you can drive a sideband like this. You could drive two sidebands to make a gate, etc. So people have demonstrated a lot of very high entangling fidelities. There's a lot of 9s on these plots. And there are other gates that people have done that I'm not showing here because they're not done in this stimulated Raman style. But there are a number of different other groups that have done high fidelity entangling gates with trapped ions that are on this order. But the challenge with this is, in order to realize a gate like this, you need lasers that are very stable, and you also need them to have very high power. They need to have sort of watt scale. They're basically off resonantly driving this transition here, and they're off resonant by many terahertz sometimes. And so you need a lot of power to get a decent Rabi frequency when you're that far off resonance. So having this really high power ultraviolet laser beam is a challenge for sort of scalability and integration. And so the other trick too is that the dominant errors in all these gates up here are still due to the laser. It's either off resonant photon scattering from this, even though we're that far detuned, or it's sort of a phase noise effect because the laser phase is not perfectly stable. So then the question is, why not just go direct? Why can't we just use microwaves? These are only gigahertz apart. Why do we go all the way up here and all the way down there? Why can't we just use microwaves? So laser-free, I'll call this spin motion coupling. Well, you don't have these photon scattering errors. You don't have to worry about laser dephasing. The microwave sources that you would have, they're stable, they're compact, they're pretty cheap compared to lasers generally. So that might help with scalability. There are ways in which you could integrate them into ion traps. And then another point is that if you do it properly, you can actually send the microwaves around to many trap zones simultaneously. A laser beam sort of shoots through a couple of ions and then it's gone. And it's very hard to sort of reuse that laser power for other ions at the same time. So why isn't everybody just doing this? Like, what's the catch? There must be something. Well, first of all, I put laser free in quotes here because you still need some kind of low power resonant laser beams as an entropy sink. So this is basically for laser cooling, for state preparation, you need something that's non-unitary. And so you need those resonant laser beams. But fortunately, all you need is sort of a microwatt of laser power, not a watt of laser power. So that's much more tractable in many ways. The second key point is that gradients are basically free with lasers because the wavelength is so short, but they're reduced for microwaves or RF. So we have to play some tricks. And then finally, sort of individual addressing, you have to be a little bit clever. With a laser, you could contemplate focusing a laser beam tightly enough that it hits one ion and not the other ions. But you can't do that with a microwave. So you have to come up with some clever ideas. And these sorts of ideas about doing laser-free spin motion coupling have been proposed for many, many years. And there are now a number of groups around the world who have been developing this technology and implementing it. And so it's exciting to be part of this effort that's really going on worldwide with a number of different schemes that people have come up with. So what's the key to getting these spin-dependent forces or spin motion couplings with microwaves? You need a non-zero gradient of the magnetic field. And so the idea is that the carrier transitions that I described, which are just a spin flip, the Rabi frequency of those goes as the magnetic field. But the sideband transitions, where you're doing the spin motion coupling, that goes as the 0-point extent of the ion times the gradient of the magnetic field. And in a typical ion trap, this 0-point extent is on the order of 10 nanometers. So it's quite small. So it's not that small compared to a laser wavelength. But if you're talking about free space microwaves, now this gradient is 10 to the 6 times smaller than a free space laser gradient. So this is really this is a problem. So what can you do? And this is a thing that was pointed out in this paper by Dave Wineland many years ago, is that if you go into the near field of some current carrying wire, you can get a larger gradient than this sort of free space gradient. So you can kind of think about it like this. If you have a current carrying wire here and some ion that's a distance d away, if the distance is much less than the free space wavelength of whatever you're driving, so if you're driving this at a few, couple of gigahertz, as long as this is, closer than a few centimeters or something, now the B field really looks more like your sort of Biot-Savart law from freshman physics. So the B field drops off as 1 over this distance, and the gradient drops off as 1 over the distance squared. And note, these are not wavelength dependent now. And so you're actually able to get orders of magnitude improvement in the gradient strength compared to what a free space microwave would have. So now, if you want to get sidebands, what you're going to do is you're going to apply currents through this wire that are where the ion is in the near field. And these are going to be strong currents. They're going to be sort of on the order of an amp or something like that at the qubit frequency plus or minus the motional frequency. And I just remind you again, this qubit frequency is sort of a couple of gigahertz and then, plus or minus a few megahertz from the qubit frequency. But so we're talking about putting a few gigahertz kind of frequencies into this wire. So what does this look like in terms of making a gate? Well, one gate that you can do is what I'll call the near qubit oscillating gradient. I'll explain why I call it that. So if we draw sort of a spectrum here, so here's DC, here's the motional frequency down at a few megahertz, and now we sort of have a break in the axis. Now here's the qubit frequency right here, and here's qubit minus motion and qubit plus motion. So basically what I'm talking about is we drive a strong current at this frequency right here, the qubit frequency minus the motional frequency, and we'll get a gradient from this strong current here. We could also drive it at this frequency, qubit plus the motion, we'll get a strong gradient oscillating at that frequency. And if we drive both this red sideband and blue sideband together, we've got these two strong gradients, you'll get an entangling gate. You have to be slightly detuned from the motion. I won't go into the gory details of this, but I'm happy to answer questions if people would like to know more. So basically, you can do a gate like this. You put sort of a few watts per each one of these tones into your trap. It works for any hyperfine qubit that you want to do. And the teams at Oxford and Hanover have both demonstrated gate fidelities. These are Bell state fidelities produced by this gate of 997. It's not super fast. It takes about 3 milliseconds to do, but if your coherence time is seconds, then this is still tractable. So what we've done in our group is actually a different version of an oscillating gradient gate. And this is what we call a near-motional oscillating gradient. And this is a scheme that was cooked up by Tyler Sutherland, our theory collaborator, and Raghu Srinivas, who is the lead graduate student on the project. And the idea now is, let's put on our gradient, not up here in the gigahertz range, but down here sort of near the motional frequency. So maybe say like 5 megahertz or something like that. You've got a strong gradient here. And then now, if you want a red sideband, you can put on a microwave tone, but you only need a weak microwave tone up here. And you put it on and you choose the detuning from the qubit such that you'll end up getting a sideband. You can do a red or a blue, and you can have both. And this allows you to get a gate. And actually, there's some subtleties about how you choose this detuning here that I won't go into. So why is this nice? Well, first of all, now your large currents that you're trying to drive are at 5 megahertz instead of a couple of gigahertz. So that's both easier technically to do, and they're lower losses, and you can get a larger B field gradient. There are fewer return currents and things like that that are induced. Second of all, if you do a gate in this manner, you can actually choose the amplitude and the frequency of these microwaves and the form of these detunings so that you can actually be robust to multiple forms of noise, not just qubit noise, but also motional noise when you make a gate like this. Finally, we've got 2 sidebands going here, but we only need 1 strong gradient that can be driven in order to do that. And so these sidebands can effectively sort of share the gradient. So it's more power efficient, I guess, if you will. The one wrinkle with this gate scheme is that you can't use one of these nice clock qubits that has very long coherence time, but this gate also provides dynamical decoupling sort of automatically for free. And so that works. And then once you're done with the gate, you can map your qubit states into the clock qubit states in your hyperfine manifold and keep things for a long time now. So I do want to point out that this was inspired by this paper here, where people were using not a magnetic field gradient, but a running optical lattice to do these kinds of sidebands. And it's also very related to a scheme where the gradient, instead of being at megahertz frequencies, is just a static DC gradient that was proposed by Minterd and Wunderlich. And people have used that scheme as well to do entangling gates. And so this is the highest fidelity result so far from the Sussex group using a static gradient scheme, which is, again, like I say, is a cousin of this scheme. So here's the ion trap in which we actually carry out these experiments. This is a trap that I made in the clean room at NIST. It's gold, electroplated gold on sapphire, and you can see these ribbon bonds here for the wires that come in. The action all happens here in the middle of the trap. So if we sort of zoom in, it looks like this. So we'll trap a couple of magnesium-25 ions right here. They're 30 microns above the surface. And then we have these 3 blue wires right here through which we flow large megahertz and or gigahertz currents to make these gradients and magnetic fields to do sideband and carrier transitions on these ions. The 2 red electrodes here are for the trap RF, which we use to confine the ions in this radial plane. And then all these little gray segmented electrodes let us make a well along this axis. I want to point out that we operate this trap at 15 Kelvin. It's not at room temperature, and there's just a couple of reasons for that. The first one is that there's reduced electric field noise. There's also reduced resistance in these electrodes too, which is a nice feature. And then second of all, because it's this cold, it cryopumps a lot of the background gas, and so the ions stay in the trap for longer, which is another nice feature for us. So now I want to talk about how we can use this trap and this scheme to also perform individual addressing. So here I'm going to show a top view of the trap. So if you remember, so we were here, we had these ions, they're kind of hovering above this portion of the trap. Now I'm going to go to a top view. So here are these ions sitting above the blue electrodes for currents and the red electrodes for the trap RF. So now if we take a strong 5 megahertz current, like we're making our gradient with, and we flow it through this electrode up here, what we find is that there'll be a B field at 5 megahertz from that at these ions. And so the qubit frequency is actually shifted by this off-resonant B field. And this is basically, it's an AC Zeeman shift. It's like a light shift. It's like an AC Stark shift would be in an atom or a superconducting qubit. You have some off-resonant electric or magnetic field, and that changes the qubit frequency. So there's an AC Zeeman shift. And crucially, because as you get closer to the wire, the B field gets stronger. There's actually a gradient of this shift, which means there's a spatial gradient of the qubit frequency. And so if what you do is use those DC electrodes on the side, those gray electrodes, and you kind of twist the crystal just a little bit so that one of them is closer to this wire than the other, now they have slightly different frequencies if and only if you're flowing this current through this wire. And so now you can address these qubits in frequency space in the same way that, for example, people do in MRI with magnetic field gradients. A key point is that the entangling gate that we have is totally robust to if these qubits have slightly different frequencies. So we can just have a twisted crystal like this and be able to address the qubits individually and then also do an entangling gate on them without hurting its fidelity. So in this way, we're able to just sort of leave the ions a little bit twisted like this and perform individual addressing of the ions with RF and microwaves without having to sort of focus them at the same time that we can do the gates. So I want to point out that others have done this kind of microwave-based individual addressing before. This is from the Zegan group, and they showed sort of crosstalk addressing one ion and leaving the other alone at the sort of 10 to the minus 5 level. So this kind of frequency space addressing can be very very clean. So how do these entangling gates that I'm telling you about perform? This is again work that Raghu Srinivas led in our group. And so I'm just going to plot here a figure where we compare the sort of the Bell state fidelities achieved from a particular fiducial initial state with several different papers. So the sort of 3 highest fidelity results that people have shown in trapped ions so far are these 3 results, which are based on lasers from Oxford, NIST, and GTRI quite recently. A very nice result. Prior to the work that I'm describing here, the best ones that were laser free were based on this sort of gigahertz near qubit gradient. And so you can see the fidelity is lower, and they're also a lot slower too. These are sort of 1 to 2 orders of magnitude slower than the laser-based gates, and that's just because it's hard to get these strong gradients. So what we were able to achieve in using our lower frequency gradient is a gate where basically the fidelity is indistinguishable from these best laser-based gates. Our best estimate is 1. Obviously, we know it's not a perfect gate, but the error bar that we're able to come up with says that 68% confidence we're above 9983. And the time that we're able to do this, the time it takes is a lot faster than some of these other ones. It's still not quite as fast as these laser-based gates, but we haven't sort of turned this up all the way. We see room that we could get this down to probably a couple hundred microseconds without too much pain. And there are actually mini trapped ion laser gates that take about that time, particularly with the terbium, which is a heavier ion, so the gates are often a bit slower. I want to point out that all of these results here were done creating this Bell state here, basically. It's a symmetric Bell state of 2 ions. And that means you can create that Bell state using just global control fields for both ions. But because we have individual addressing, we're actually able to make an anti-symmetric Bell state, which is not symmetric under exchange. It requires individual addressing to make this state. And so we demonstrated that. And so it only takes a little bit more time to do the individual addressing. And the fidelity here is good. And to my knowledge, this is the highest fidelity anti-symmetric Bell state that anybody's made in any technology. So what we have now is we've got this nice demonstration of a laser-free qubit technique where the gate fidelity is really comparable to the very best laser-based gates. And these are the best gates in any quantum technology. Plus, we can do individual addressing and make these sort of anti-symmetric states. So this is sort of a very promising tool for being able to do real quantum information processing in this using these magnetic field gradients. So now I'll change gears and go on to the second portion that we're talking about, where we're integrating photon detectors into our traps. So typically, the way that people detect fluorescence from an ion to perform a measurement is you have your ion in a trap, you shine a laser beam on it, it scatters photons in all directions. You have some sort of high numerical aperture objective that collects a subset of them and sends them up to a camera or a photomultiplier tube to count them. And if you have more than one ion, the ions are sitting out. And so now this becomes a little bit more challenging, because now you need an objective here that has high numerical aperture, works for UV light. It needs to have a large enough field of view to encompass all of these ions, needs to have a large enough magnification that you can distinguish these two ions from each other on a camera, say, needs to have low enough distortion that this ion's photons don't hit that ion's camera pixels. This is a tricky optical design problem. It's not insurmountable, but it's non-trivial. And then secondly, once you start to scale, now you have this issue where you have an objective like that, but the objective's diameter is much, much larger than its field of view. And so if you're trying to image a trap down here, you basically can't get these close enough. You'll have blind spots in your trap that can't be used. And what if your trap has limited optical access or no optical access? That's another sort of challenge. So one idea is, why not, instead of this, use trap integrated photodetectors? They could be self-aligned, they could be spatially resolving, and this might help with scalability. So what do I mean by that? Well, let's look at this proposed trap integrated detector architecture. The idea would be that you've got an ion trap here, and you've got ions hovering above it, and then you have different detectors in different zones that are actually fabricated into the trap along with the trap electrodes. And each one only needs to collect a few % of each ion's fluorescence. And now if you do this, you can read out all these ions in parallel. Each one has its own private detector. And now you've got scalable sort of trap integrated fluorescence readout. You don't have any optical elements that you have to worry about, objectives or lenses or mirrors or anything like that you're trying to make. So what kind of detector would you want to use for that? What we have chosen for our work are what are called superconducting nanowire single photon detectors, or SNSPDs. But I want to point out that there are two efforts going on at MIT Lincoln Lab and at Sandia to actually do this kind of thing with avalanche photodiodes in silicon. And they've had some nice recent progress. This is the Sandia paper, which has just come out recently, and Lincoln is writing up their results as well. So they have some promising initial work from both places. But so tell me, well, let's talk about what this detector is and how it works. So the idea is that you have a small nanowire, it's sort of 100 nanometers wide kind of thing, and you meander it back and forth to cover some active area. And this runs, it's superconducting, it runs cryogenically, sort of below 4K-ish. And you flow a small DC bias current through it at some sort of microamp type level. And just very coarsely, what happens is if a photon with sufficient energy comes in and is absorbed in the nanowire, it actually breaks the Cooper pairs locally, and you get a hotspot. And the hotspot formation is aided by this bias current. It's a function of this bias current. And so as a result, then you get a voltage pulse that comes out. And then after a little bit, the hotspot thermalizes again, the detector has reset, and you're ready to count another photon. So this is an actual trace that I've taken in the lab. This gives you a very nice high signal to noise ratio click. This is representing the arrival of a single photon on this trap. So you have single photon resolution, very cleanly, good SNR. So why are these detectors nice? Well, you can count photons at sort of millions of photons per second. The dark count rates can be way below 1 count per second, which is very nice. The active areas that you can get of these detectors are commensurate with what one would want for an integrated detector in an ion trap. And the quantum efficiency for photons arriving can be basically close to 1. So these are very nice detectors generally. But there's some questions about them for us. So first of all, what's the effect of the trap RF, right? We've got this little microamp bias current. Now we've got the trap RF, which is actually tens of volts, you know, at hundreds of megahertz, tens of megahertz right nearby. What's that going to do? We need to operate fairly warm because the ion trap doesn't go much below 4 Kelvin. Can we get them to work well in the ultraviolet? And then finally, like, will the clicks here have an impact on the ion that's negative? We can't trap an ion above a detector like this. So we went ahead and fabricated a detector like this. This is work that Varun Verma from the Faint Photonics group and I fabricated these traps in the NIST clean room again. And so here's this trap, and if you zoom in on the sort of the active area there, what you'll see is we've got the trapping RF in red. There's the detector here in green, and we can trap an ion. We can move the ion around to any kind of position from far away from the detector to right over the detector. And then when it's over the detector, we can shine a laser beam on it. It'll fluoresce, and we count some of those photons. And so the detector collects about 2% of the photons that come from the ion, and it operates at 3.5 Kelvin. So it's colder than most ion traps, but it's still a comfortable temperature from cryogenic technology standpoint. So just to show you a picture, this is a different device of what the actual nanowire looks like. You can kind of see here these long, skinny, meandering nanowires that go up and down. And the detector is actually recessed a little bit below the trap electrodes, which is nice. It shields it a little bit from stray light. So how does this detector perform with trap RF? So these are data that were taken by grad student Susanna Tadero. And here's an example where what I'm showing here is the bright count rate and the dark count rate of the detector with either a laser illuminating it or not illuminating it as a function of the bias current that we flow through the detector, the DC bias current. And we didn't do this with an ion. This is just with laser illumination for this test, because when you turn the RF off, you can't hold an ion in place. So with the RF off, what you see is that first the detector doesn't count anything. And then at a certain stage, the detector efficiency rises and plateaus. And so above a certain bias current, the detector will basically click always when a photon hits it. And the dark counts stay low, and they sort of rise as you get very close to this maximum bias current. Now, when you turn the RF on, the shape of this curve changes, and the maximum bias current you can apply changes. But the main point is that, first of all, the thing still works. Second of all, the maximum sort of count rate that you get, this is the same illumination, is almost as good as you can get with the RF off. And if we basically try and understand what's going on here, we can actually fit a model that assumes that the trap RF is inducing some RF current in the detector. And if we fit that model, we get this blue curve here. So there's quite good agreement that we think we understand why the trap RF is affecting this detector. And we're currently working on fixing this by having better electrical shielding for the detector to protect it from the RF. So with this, we're actually able to, we know the solid angle, we can tell about the quantum efficiency, and so we can actually then use the trapped ion and hold it above the detector and count photons from the ion. And we can actually use the ion as a calibrated photon source for this detector and determine that we have about 48% detector quantum efficiency for 313 nanometer photons. So this is better than is available with any photomultiplier tube or camera. So that's kind of nice. So what kind of qubit readout fidelity do we get with this? So what I'm showing here is a plot of 100,000 trials, half of which we prepared the ion in the bright state where it will fluoresce, and half where we prepare it in the dark state. So what you expect to see is basically, and this is a log scale here, is a Poissonian distribution of counts for dark and a Poissonian distribution of counts for bright. And the idea is that you sort of pick a threshold in between them and say, aha, well, any trial that I got more than this many counts, we'll say that was bright. And if we got less than that many, then we'll say it was dark. And so what you see is that there's some little tails. There's some times where we prepared a bright ion, but we didn't count photons, or times we prepared a dark ion, but we did count photons. These are actually can be ascribed to the atomic physics properties of beryllium. They're not actually due to the detector. And so what this means is we can actually vary the amount of time for which we collect photons. And what we find is we get sort of a maximum readout fidelity. If we go to 125 microseconds here, we have a qubit readout error of basically 1.2 times 10 to the minus 3. But then there's a trick that we can play, and that is that we know when the photons are arriving, not just how many photons we counted in this time. We can actually see, we timestamp them to the nanosecond of when they arrive. And so we can actually use the photon arrival times to get a better state estimation using some Bayesian techniques. And so here you can see, as a function of our Bayesian confidence threshold, we have different readout errors. We can actually get to now in 46 microseconds on average, we have a readout error of 9 times 10 to the minus 4. So these are the best that's been done in beryllium in any setup, including with traditional large collection optics and photomultiplier tubes. So in the few minutes that we have left, I'll talk to you a little bit more about how we're envisioning taking these kinds of technologies and making a fully integrated ion trap quantum processor. So first, I'm going to tell you about the need for 2 ion species in a trap. And the first thing I'm going to tell you about is what we call sympathetic cooling. So let's say you've got 2 ions, and they both have your qubit data, and they're sitting in a trap. And what happens is, over time, there's electric field noise that just comes from charges wiggling around on the surface of the trap electrodes. And that slowly excites the ions. So their motion is no longer near the ground state. And so as the motion gets more and more excited by this causes errors in gates that you're trying to run on these qubits. So, what's the solution? Well, you think, well, of course, you just laser cool. The problem is laser cooling destroys the qubit information that you're holding in these ions because it changes the electronic state of the ions. So you can't laser cool these ions. So what are you going to do? Well, one thing that you can do is you can actually trap these data ions in the same well with a helper ion. And you laser cool the helper ion instead. So the helper ion is a different species. It might be a different isotope, or it might be a different set of levels, or it might be a whole different kind of element altogether. But you choose it so that its lasers are not resonant with the data ions. So now, once everything gets hot, now you put on the helper laser. That cools the helper. That also cools the data ions because they are coupled to the motion of the helper via the Coulomb interaction. And so now you're able to cool off these data ions without disturbing the qubit information that they hold inside. So this is really crucial for running longer algorithms, and after you've transported ions around in this kind of quantum CCD architecture. So that's one reason why 2 ion species are nice. The other reason why they're nice is for what we call mid-circuit readout. So let's say you've got a data ion over here, and you've got another data ion over here, and this one you want to measure, and this one is a memory. You're storing this for later. So what you do is you shine on a laser beam, and so this data ion starts fluorescing. And if any of the photons from its fluorescence or stray light from the laser hit this ion over here in the memory zone, you've got a memory error. And to keep this at the sort of 10 to the minus 4 level even, these need to be like a millimeter apart. And so this is a serious thing that needs to be considered. So what can you do? Well, you can put a helper ion in with the data ion that you want to read out, and you can use what we call quantum logic readout. And this is a technique that's used, as I mentioned earlier, in trapped ion clocks a lot. And the idea of quantum logic readout is that you basically make some entanglement between the helper ion and the data ion, and then you measure the helper ion, and now the laser scatter from the helper ion is not going to perturb the data ions. And if you do this entanglement between them in the right way, this can be a QND measurement. And so you can do repeated rounds of measurement to get the fidelity of this measurement higher and higher. This entangling operation doesn't necessarily have to be brilliant fidelity as long as it's non-demolition. And now these photons, this ion over here, will not be disturbed by them. So this kind of thing is going to be crucial for implementing error correction, because if you're going to do error correction, you're going to be doing most likely mid-circuit measurements. And so that means that there's going to be a lot of this kind of crosstalk memory error. So now let's think about how laser-free gate operations and mixed species might come together. So first of all, laser-free gate operations are very nice because we can do them in parallel. So how does that work? Well, let's say now, instead of just what we had before with one well with 2 ions in it, we've got several different zones in the trap. I'm showing 3, it could be 1,000. And the trap electrodes run underneath all of them. And so now if you drive the sort of strong gradient and weak microwave these electrodes, they will make fields and gradients in all of these different zones at once. And so basically we have one drive power that's effectively recycled to perform entangling operations simultaneously in many zones, because the current is not changing through this wire. So the gradients are basically the same at all of these. And our scheme is robust to slight variations in these parameters. So now, what about if you didn't want to do an entangling operation on all of the ions, but just some of them? So if you want to do a dressing, you just change the local well confinement with some static electrodes. So now if we change this central well here, so this central well goes from being confining to a little bit less confining. Now when we drive these drive currents, the interactions will be resonant here in these wells, but the sidebands are not resonant with these motional frequencies because they've changed. And so now these ones just, they don't see an entangling operation drive. Now, if we want to do mixed species entanglement, like for the readout that I just mentioned, now all we have to do is add 2 more weak tones here. We're just sharing our strong gradient again, but now we've got microwaves for the green qubit and microwaves for the red qubit that are at different frequencies. And now we're running this entangling operation, and so we can do all the things that we want to. These gates that I'm talking about are robust to if the fields are not precisely calibrated in all of these different zones simultaneously. They can tolerate a fair amount of that. And so the idea is we can do laser-free entangling gates. We can do readout and actually state preparation with these helper ions. That means that we don't actually need any lasers at all for the data ion species, because they can be sympathetically cooled by the helper ions. They can be read out and state prepared by running these laser-free entangling operations. And so now we're free to choose a data ion where the lasers might be a real pain. And we are free to choose a help, but that has a really good qubit, for example. And we are free to choose a helper ion where the helper has very friendly laser wavelengths that we like to work with, but might not be the best qubit for whatever reason. So, so there's some further pieces that we'd want to integrate into a trap like this. And this is work that's been done by other groups. One thing would be integrated photonics to actually deliver the laser light to the ions, not through a free space beam, but through waveguides that go through a trap. So these are images here from this first paper where a waveguide's going through the trap and is firing laser beams up out of these grating couplers to the position where an ion sits above the trap. And you can actually scale this so that there's waveguides to many different zones where you have this control. There's people working on multiple pixel SNSPDs in order to, have arrays. You could use this kind of thing for arrays in a trap. There are even people who are working on putting ion traps on top of a CMOS chip, and the CMOS chip underneath contains a DAC, and so, or mini DACs, and so all of the trap electrodes are driven by DACs on these chips. So you have a serial connection to the trap, and the trap makes its own confining potentials. So if you put all of this kind of together, you have sort of a vision like this for a unit cell of an integrated ion trap. So the sort of the basic building block looks like this. So we've got 2 ions as the basic unit. And we have a helper ion here, which is chosen because it has sort of friendly laser wavelengths. And then we have a data ion for which there are no lasers at all. And it's chosen to be a good qubit, and we don't care about what its laser wavelengths are. And then this is great because this this data ion here is totally immune to photon scattering because there'll be no resonant light around. So now we can harness the sort of full beauty of its really long T1 and really long T2 and the ability to do these really high fidelity laser-free entangling gates. We'll need microwave electrodes, and we can put high current electrodes in a lower layer to make even stronger gradients. We can do the laser-free control like that. And then the helper ion will need some laser beams. We'll deliver those laser beams through integrated optics. And the helper ion will be chosen so that these are only low power laser beams that have friendly wavelengths in the visible or the IR. And then finally, we can put an integrated photon detector under here to count fluorescence photons from the helper ion and measure its state. And then we'll use this laser-free quantum logic to measure the state of the data qubits. And so this is just, this is one qubit basically, and plus its helper. And so then the whole system, there's no external components to align. There's no laser beam alignment from outside. There's no anything like that. You just plug fibers into your chip, you wire bond to your chip. Everything is self-aligning now, and high fidelity in theory. So now, if you want to scale this up, then this would be sort of our vision for a scalable system where you've got mini qubits. They're all sort of trapped around in different places. And then you'll move this data qubit around to interact with whatever data qubit elsewhere it needs to talk to in order to make the qubit connectivity graph for your algorithm. And you can bring the helper ions along with the data ions or whatever. You can leave them in place and the data ions come to them. But basically all of the control, all the readout is chip integrated, it's lithographically defined, it's high stability. You could think about stamping these out to make many, many zones. So that's sort of our vision for scalability. So with that, I'll thank you for your attention. So this is a picture of much of our group. There's about a dozen new people since this group photo was taken. This is the view of the beautiful Flatirons, which is this is the view outside the door of our lab here in Boulder. And I particularly want to thank all the people who worked on the results I've shown you today. In particular, Raghu Srinivas, who led the laser-free gate work. Sean Bird and David Alcock were essential in this as well. Tyler Sutherland, the theory collaborator on that. The fidelity analysis was spearheaded by Alex Kwiatkowski, who's a grad student. And Varun Verma, in particular, has been my partner in crime for many years on the integrated detector work. And Susanna Tadaro did the heavy lifting on measuring it with the trapped ions. And of course, there are a number of us who are staff scientists in the group, and we appreciate funding from these sources and others as well who prefer not to be listed on slides. So with that, I'll thank you for your attention. I'm very happy to take questions that you might have.
Well, thank you so much for that fascinating talk, Daniel. That was really, really interesting to see the things that you can integrate, that you can get away with RF controls, and how many lasers you've gotten out of the system. So if anyone has questions, please drop them in the chat and I can ask Daniel. In the meantime, what we have so far is, you did a very clear presentation. Didn't seem like there was much clarification needed, but there were a lot of people wanting gory details. So can I encourage you to go back to the slides talking about the gradient control of the motional state?
Sure. Hang on. Let me release my laser pointer so I can
Okay.
go back to those slides. All right. So which slide in particular? So like this slide here? Are we talking about
let's see. So,
are we talking
yeah,
about
I believe
like this one here?
Yeah, a little further back. Yeah, this stuff. Yeah. I think this is where we were, where we wanted to be. Okay. So I guess the first question is actually mine, but there were a number of questions about this. So I was seeing that are you thinking of this this simultaneous driving? Sounds like you're mixing the signals together somehow. Is there a nonlinear element doing that, or is this more like kind of like a
No.
Raman with lower frequencies?
I mean, so The whatever the nonlinear element is the atom itself. There's no actual mixing of the signal. So the frequency spectrum that we're applying to the trap is just this. There's the strong gradient at 5 megahertz, and then there are two weak microwave fields right here. And basically, what happens, the way you can think about this is that the qubit transition is magnetic field sensitive. And so you're basically, with the gradient of this magnetic field here, makes it so that you have a spin-dependent force on these, on the ion that's oscillating back and forth, non-resonant, off-resonantly with the motion. But what these two fields here do is they kind of flip the spin. The red and the blue field actually, in a physical picture, the qubit spin in the lab frame is doing this. It's rotating this way and then back this way and then this way and then this way. It's going back and forth. It's being modulated. And so the spin is being modulated back and forth at just the right frequency so that the gradient, which is off resonant for driving the motion, actually becomes on resonant because the spin is catching up with the frequency difference that you would need. I don't know if that helps you. It's a challenging thing to understand physically, but that's what's going on.
I think that helps, and that also clarifies why you consider this to also be dynamical decoupling that you get for free in this kind of scheme.
Exactly. So if these microwaves are quite weak, you're basically just doing this back and forth. And if you're driving them stronger, you do this. And if you drive them at just the right strength, the qubit spends half the time spin up and half the time spin down as it's doing this. And so when at that sort of magic driving amplitude, you're now are resistant to basically low frequency dephasing noise, which is nice. Another technical point about this interaction is most trapped ion gates that people do are a sigma X interaction. And that interaction does not commute with sigma Z noise. So if you have like a qubit frequency offset or noise, it doesn't commute and that will mess up your gate. This interaction is, we can choose what this delta detuning is such that it actually is a sigma Z interaction. So it commutes with qubit frequency offsets. So the idea then is that you can basically, even if your qubit frequencies are not exactly what you think they are, like when in this individual addressing configuration, the gate commutes with that. So you do one section of gate, you do it halfway, then you flip the spins like a spin echo, and then you do the second half of your gate, and you basically unwind everything because the Z, noise or offset on the qubit commutes with the ZZ entangling interaction.
Makes a lot of sense. And I think that refers to another question about reducing noise in the system. So there was another question about this, specifically for this. How do you make sure that both the red sideband and blue sideband applied to both of the ions are of the equal Rabi rate, which should be crucial for high fidelity gates?
Yeah, you're absolutely right about that too. So again, the way we do these gates are so-called geometric phase gates, which basically involve exciting and de-exciting the motion in a state-dependent way, somewhat off-resonantly. And so what you can do is if you do a gate like this, and you, instead of just doing a gate in one long interval, but you split it up into a gate that you do some way, and then you flip either the qubit spin or the phase of your gate drive, and then you do the second half of the gate, that technique can actually undo some of the effects of having the Rabi frequencies be not quite what they need to be calibrated as. And we actually go to higher order with that. So we actually do what we call an 8-loop gate. And so we are decoupled to third order, both from Rabi frequency offsets and motional frequency offsets or drifts. If the motional frequency is not exactly where we think it is, which again will impact the Rabi frequency. So there's a lot under the hood here going on. If you see this reference in the lower right, this Nature paper is where this is published, and there's a lot of gory detail in the supplementary material. If people are interested in really drilling down, I encourage you to look at that.
Oh, that's great. Yeah, I was asking for the gory detail since you suggested. I thought I'd put that to the YouTube chat.
Yeah.
So another question that's related to this is, what is the bottleneck for making these gates faster?
How much gradient you can get, basically. So right now, so we were somewhat conservative with this. We were driving sort of a little more than an amp per electrode in the trap. And that doesn't seem to be limiting. We've done gates now down to 500 microseconds. And that was sort of right before COVID shut us down. And then since we've come back from COVID, we've been working more on this mixed species thing rather than trying to speed this gate further. But basically, part of the limiting factor is in order to run this gate, you have to ramp the gradient on and off, and you have to ramp the microwaves on and off in a sort of a precise way. And if the faster you make those ramps, the more timing sensitive you are. So our ramps are sort of somewhat slow. So we spend 160 microseconds of our total gate time on ramping stuff up and down with all these mini loops that we have. But if we wanted to, we could make that faster. And then if we just drive a stronger gradient, we'll make that faster as well. I mean, I think realistically, you're never going to get a 10 microsecond gate out of this. But you could see 100 microseconds or 200 microseconds, I think, would be sort of the limit of what you're going for. But again, if your qubit coherence time is seconds, then that's tolerable perhaps.
So you alluded to another question I had, which was you're putting an amp of current into those things. That's a lot. So it looked like you were using gold traps, or would using a superconductor or anything, any other kinds of materials help you with those kinds of current densities without or what is the kind of detrimental effects you get, I imagine, from like joule heating?
Yeah. So actually, this is thick electroplated gold. It's 6 microns thick, and a big reason for that is that there's lower resistance, there's lower resistive loss. We also run cryogenically, and we get about a factor of 10 lower resistance with this gold cryogenically than at room temperature as well. The actual joule heating in this trap is only a tiny portion of this. So we apply, a few watts, but we only dissipate some 100 milliwatts or something like that in the trap itself. Basically, the drives, we have a short circuit termination just off chip. And you can actually see it right here. So these electrodes come out and they're just shorted to ground, right there and there. So basically all the power comes in and is reflected back out. So the dissipation is all happening in impedance matching circuits and circulators outside the vacuum chamber, actually. So only a small amount of it is dissipated here. We have seen as we drive these things harder that the chip will heat up a little bit. And that's basically just the glue between this chip and the pedestal being not as thermally conductive as would be ideal. And since we put this system under vacuum, we've got better techniques for doing that for thermal management, but we haven't tried it out. We've done tests with traps like this where we've run 3 amps DC CW through these things, and the trap doesn't blow up. So we feel good. The trap will rise about 10 Kelvin in temperature, so you'll have to calibrate for that, but it's not intractable. Superconductors, we've looked at that. The critical current densities just aren't there. It's just really hard for so these electrodes are like 13 microns wide. And you're not gonna a thicker film of a superconductor doesn't help you because you're all just within like penetration depth, and so really you have to make them a lot wider to get the gradients, and so I think electroplated gold seems to be a pretty good option.
Okay, cool. That's very good. And I think we just got one more question, and that's for your multi-species RF pulses. Do you need different pulse waveforms to control those different species, or this is just the frequency, I suppose?
So I mean, we'll synthesize them separately. You'll have different amplitudes and stuff, but in general, it's the same. Basically, if you've got something like this here, where you've got your gradient, and then you've got your 1 qubit frequency, and you've got 2 tones that are detuned, and you pick their amplitudes and detunings just so. Now over here, you'll have a second set of tones with their amplitudes and detunings picked just so, centered around the frequency of the other qubit. And you basically, you have to depending on how you're doing stuff, you either do or don't have to match Rabi rates for the sidebands on the two systems. I mean, you can do a thing if you're trying to do an entangling gate between the two, then you have to match the Rabi rates. If you're just trying to do the quantum logic stuff, you can actually use this stuff to sort of swap the data qubit information into the motion and then turn it on for the other ion and swap it from the motion into the other qubit and then read that. And that's not as noise robust, but because you can do repeated rounds of this measurement because it's QND, that it doesn't really matter. So you get 90% fidelity in one shot. So what? Do it 5 times. You've got all the 9s that you want. So
that's interesting. I mean, there's so many control knobs. It's kind of baffling dealing with all these frequencies and sidebands and everything else. And so we have one more question that snuck into the chat. So this is all I'll hold you to today. But this concerns your last slide where you showed the completely integrated system. So this is the scaled ion trap architecture, and there was a question about how can one achieve all-to-all connectivity between all the qubits on the chip in that scheme?
Well, you don't achieve it all simultaneous. It's not at once. But I mean, so I would say all-to-all connectivity is maybe not the phrase that I would use as the ideal, because all-to-all connectivity, you gotta pick, you've got to drive one of those connections and not drive all the other ones and have crosstalk, right? So what I would describe it as any to any connectivity. So basically, if you want to connect this ion here with any other ion in the trap, you just move them together into a zone, have them interact, and now you move them apart to other places. So you're not connected to all other ions at the same time. That would be too much to handle. The idea is that you pick, and you can do this in rounds. So you're like, okay, one round, everybody, ion 12, ion 47, you guys need to be entangled. Also, at the same time, ion 16 and ion 17, you guys need to be entangled. So you move all these pairs together, you run a global round of entangling that does all these entangling operations, and you're like, okay, that was great. Now people go entangle with the other ions that you're supposed to do in the next round of the algorithm. And then everybody is reshuffled, and then you do the global entangling, etc. And because you can do all the entangling gates in parallel, it helps. Like, so, if the entangling gate takes a few hundred microseconds, that's okay, because you can do many of them at the same time, as opposed to waiting for ions in turn to sort of be freed up to use the laser zone where the entangling lasers are driving things.
Okay, well, thanks for the clarification. I'm getting a lot of applause and thank you from the chat, so thank you very much again. And I'd like to ask if you have any last words, anything you'd like to plug, any job openings, etc.
Yeah, well, I mean, we're always looking for good graduate students and good postdocs in our group. So if you Google NIST Ion Storage, you'll find our webpage, and you can reach out to me or one of the other staff scientists. And I really appreciate everyone listening and hearing about a topic that's maybe a little off the beaten track for some of the Qiskit seminar history, but I hope you've enjoyed it, and I hope you've learned something about some of the work that we're doing.
Yes. Thank you so much again, Daniel, and it was a pleasure hosting you for this Qiskit seminar. And I'd like to encourage our listeners to subscribe to the Qiskit YouTube channel, where you can not just get recordings of these seminars and notifications when we're going live, but all kinds of other resources we have available for the Qiskit community. And with that, I've been your host, Nick Bronn, and I'm signing off, and see you next week.